welcome back to the channel. Thank you so much for being here and for spending your time diving into the universe with me. If you enjoy these deep, science-based explorations, it really helps when you like the video, subscribe, and share it with someone who you think would love this kind of content. It makes a huge difference for the channel. I'm also really curious about you, so let me know in the comments, what time are you watching this and where in the world are you right now? All right, let's get into before the first second of the universe. Long before formal science, human beings stand beneath the night sky and ask what it is and how it began. In every region of the world, people learn to track the patterns above them, the slow drift of constellations from season to season, the regular return of certain bright points, the rare arrival of comets and sudden stars that appear and fade. The sky becomes a calendar, a clock, and a quiet record of change that unfolds on a scale far beyond any human life. From these patient observations, entire stories of origin and purpose grow. In river valleys, along coasts, and across wide plains, rulers and priests connect the positions of planets and stars with harvests, floods, and wars. They imagine a layered universe with Earth below a dome of sky above and realms beyond that only gods can cross. Creation myths describe beginnings that echo the social world on the ground, a single powerful being, shaping order from chaos, or a family of deities arguing, dividing space, and assigning realms to one another. The universe is described as finite and structured, with a clear center and a clear hierarchy. Time often has a direction that mirrors a human life, with a birth, a flourishing middle, and an eventual decline or destruction. Some traditions, however, describe something different. In parts of ancient India, early philosophical schools begin to consider the possibility that the universe has no true beginning or end. They picture cycles of creation and destruction, long ages in which worlds form, dissolve, and form again, not once, but endlessly. In later Hindu cosmology, vast cycles called kalpas describe repeated universes, with each cycle stretching over spans of time that dwarf any human history. Early Buddhist thought speaks of countless world systems arising and passing away with no single privileged first moment. The Stoic philosophers of ancient Greece describe a cosmos that periodically burns in a great fire and is reborn from its own ashes again and again. Alongside these cyclic ideas, another thread appears. The atomists in Greece imagine that all matter is built from tiny indivisible units moving through a boundless void. In this view, space extends without limit in every direction, and there is no preferred center. Time also stretches without bound, with no special moment of creation. Worlds can form wherever the right arrangements of atoms occur, persist for a while, and then break apart, while new worlds arise elsewhere. This infinite universe bears no mark of an origin that can be pointed to. It simply exists, uncreated and eternal. Across cultures, two broad pictures of the universe take shape. One sees the cosmos as something that began whether through a divine act or a rare transformation, and that will one day end. The other sees the cosmos as something that cycles or simply persists with no fundamental beginning or final moment. In both cases, the stories are grounded in what people can see: the rising and setting of the sun, the phases of the moon, the return of constellations, the occasional disruption of a comet or an eclipse. For many centuries, these observations are made with the unaided eye. No one yet has lenses that can reveal faint galaxies or distant clusters. Still patterns emerge. The stars maintain their shapes relative to one another, turning as a rigid pattern from east to west each night. The planets wander along a narrow band of the sky, sometimes brightening, sometimes fading, sometimes reversing direction against the backdrop of the fixed stars. Eclipses can be predicted, and their cycles can be recorded on stone and clay. Gradually, the heavens begin to look less like a stage for arbitrary events and more like a vast but ordered system. This recognition does not immediately erase mythic explanations, but it begins to create a quiet tension. If the motions of the sky follow regular rules, then perhaps the origin of the sky is also governed by some deeper order, however distant and unknown. As philosophical schools grow in ancient Greece, thinkers start to separate questions of myth from questions of mechanism. They ask not just who made the cosmos, but what the cosmos is made of and how its parts hold together. Some suggest crystalline spheres carrying the stars around the earth. Others propose a rotating fiery shell. Still others hint at a central fire hidden from direct view. These models remain rough and incomplete, but they already reflect an important shift. The universe is no longer only a story of will and intention. It is also a structure that can be described and perhaps quantified. Yet, even as ideas about mechanisms become more precise, the deepest question remains untouched. Whether the universe cycles without end or persists forever or is set into motion by a singular creative act, there is still an assumption that the world as a whole either has no origin that needs explanation or has an origin that lies entirely in the realm of the sacred. The stars themselves do not yet seem to provide a way to test one picture against another. The night sky is filled with light, but it also contains vast stretches of darkness between the visible stars. To many early thinkers, that darkness can simply be the empty spaces between lights or the limits of human sight. Only much later will that darkness become a clue that challenges the idea of an eternal, unchanging, infinitely populated cosmos. For now, humanity stands at the threshold of a new kind of inquiry. Observations have become detailed enough to suggest that the heavens follow consistent patterns, but instruments and mathematics are not yet advanced enough to turn those patterns into a full physical model. The universe still feels fixed and eternal on human timescales. Mountains and oceans do not obviously appear and vanish. Stars do not obviously ignite and fade, and the constellations look the same from one generation to the next. It is natural to imagine that the cosmos itself is static, either endlessly repeating or simply existing without beginning. In this setting, the first precise laws of motion and gravity will soon arrive, and with them, the first attempt to draw a complete quantitative picture of the universe. That picture will look calm, balanced, and reassuring, but within it, a subtle instability will already be waiting hidden in the same sky that has guided human stories since prehistory. In the 17th century, the quiet patterns of the sky begin to meet a new kind of description. Instead of stories about spheres and fires, a single set of rules is proposed to govern falling stones orbiting moons and the paths of planets across the zodiac. Isaac Newton formulates laws of motion and a universal law of gravitation that connect the pull felt on an apple to the pull that holds the moon in its orbit. In his great work on mathematical principles, he presents a universe in which every piece of matter attracts every other piece with a strength that depends on their masses and on the distance between them. The details of the calculation are difficult, but the core idea is simple. Gravity is the same everywhere, and the same rules apply on Earth and in the heavens. This step quietly removes a wall that had stood for centuries between the sky and the ground. The universe becomes one continuous physical system. Once these rules are accepted, it becomes natural to ask what kind of universe they describe. If every piece of matter attracts every other, then a finite cloud of matter should not remain in a calm state forever. It should begin to fall inward, collapsing into a dense cluster. Yet the stars in the sky do not appear to be falling together into a single point. The constellations remain stable over human lifetimes, and there is no obvious sign of an all-consuming gravitational collapse. Newton is aware of this tension. To preserve a static universe, he adopts a picture that echoes some of the ancient atomists, even though the physics is very different. The cosmos is imagined as infinite in space, filled more or less uniformly with stars and other matter, extending without bound in all directions. In such an infinite distribution, there is no privileged center, and the pull from distant matter can balance and cancel in such a way that no part of the universe is drawn uniquely inward. The gravitational forces from all sides can add up to a near equilibrium. In this way, Newton and those who follow him can reconcile a universal attractive force with a universe that does not obviously collapse. The result is a static, eternal cosmos, held in place by a delicate balance that is rarely spelled out in full detail, but is assumed to work at large scales. Philosophical and theological views at the time support this picture. Newton holds a belief in a creator who orders the universe, but he does not place that act at a specific moment in measurable time. Time is treated as absolute stretching without beginning or end, ticking at a steady rate everywhere. Space is treated as an unchanging stage on which matter moves according to the laws of motion and gravity. The combination of infinite space, eternal time, and a uniform distribution of stars produces a universe that has no birth event in physical terms. It simply exists, ordered by fixed laws. For many thinkers, this is a satisfying resolution. The same equations explain the orbit of Jupiter and the fall of a stone, and the same infinite framework can host all future discoveries. Yet subtle difficulties begin to appear when the implications of an infinite static universe are examined more carefully. One problem arises from the night sky itself. If the universe is infinite and filled everywhere with stars similar to the sun, then along any line of sight, one should eventually encounter a star. Even if many stars are blocked by dust or other matter, an infinite number of stars in an infinite space ought to make the night sky exceedingly bright, almost comparable to the surface of a star when averaged over all directions. Instead, observers see a sky dominated by darkness, punctuated by discrete points of light. This tension is later named as a paradox, but its roots lie already in the contrast between Newton's static universe and the simple visual fact that most of the sky is dark. Various responses are attempted. Some suggest that distant light is absorbed by intervening matter. Others note that stars have finite lifetimes and might not fill every region forever. However, when the implications of these ideas are followed through, new questions emerge. If intervening matter absorbs light over very long times, it should heat up and eventually radiate returning light to the sky. If stars are born and die, then matter cycles through different stages, and the assumption of an unchanging universe becomes less secure. A second difficulty involves the stability of the infinite distribution of matter itself. Mathematicians and physicists realize that even in an infinite space, small irregularities in the density of matter can grow under gravity. A slightly denser region pulls more strongly, attracting additional matter and becoming denser still. Over sufficiently long times, this process could create structures or lead to runaway collapse in some locations. The idea of a perfectly uniform, perfectly balanced universe begins to look fragile. However, the observational tools of the time are limited. Telescopes grow in size and quality, revealing new objects such as nebulae and star clusters, but they do not yet provide a clear statistical map of the universe on the largest scales. With no direct evidence that space itself changes with time, and with no way to measure the distances to faint smudges beyond the Milky Way, the static model endures. It serves as the default background for astronomical thought. Within this framework, change is local, not cosmic. Stars form, shine, and fade. Comets appear and vanish. Planets orbit and sometimes realign in ways that produce notable conjunctions. Yet, the overall structure of the universe is treated as fixed. The Milky Way is regarded by many as the entire universe, with dark gaps between its clouds of stars marking true emptiness rather than vast distances. This view makes the problem of the dark night less pressing because the total number of stars is not yet understood to be enormous on a cosmic scale. Even so, traces of unease persist among those who push the mathematics of gravity further. They find that a truly infinite, static, self-gravitating distribution of matter is not a simple configuration. Tiny perturbations can have large consequences over long times. There is a mismatch between the desire for a calm, eternal universe and the dynamical tendencies of gravity as encoded in the Newtonian laws. For the moment, the mismatch can be set aside as a technical issue or an incomplete calculation. The larger narrative of a universe that simply is, with no physical beginning and no global evolution, remains intact. It fits the philosophical preferences of the time and aligns with the idea of an orderly creation maintained by consistent rules. Yet the sky is beginning to offer hints that this picture is incomplete. Faint nebulae whose nature is still unclear scatter the heavens. Some appear as diffuse clouds within the Milky Way, while others are more compact and enigmatic. Their spectra and motions are not yet well understood, but their mere presence suggests that the universe contains structures whose scales and distances might go far beyond the local stellar neighborhood. If these objects lie outside the Milky Way, as some thinkers quietly suspect, then the universe is far larger and perhaps more complex than the standard static model assumes. For now, the static clockwork cosmos holds. Time and space are absolute, the laws of motion are fixed, and gravity binds everything together in a grand but essentially unchanging arrangement. However, embedded within this orderly picture are puzzles that do not fade with better measurement. The darkness of the night sky, the potential instability of an infinite gravitating medium, and the ambiguous nature of distant nebulae form a set of clues. They will eventually converge with a new theory of gravity that does not treat space and time as a passive stage, but as active, dynamic participants in cosmic evolution. When that happens, the old static universe will begin to give way, and the question of whether the cosmos had a beginning in time will return in a sharper and more demanding form than ever before. At the start of the 20th century, the quiet tension inside Newton's static universe meets a new description of space-time and gravity. Albert Einstein examines the way that measurements of distance and duration depend on motion and on the speed of light. Special relativity. His first major step shows that there is no single universal clock that all observers can share. Instead, moving observers experience time at different rates. A fast-moving clock ticks more slowly than one at rest and lengths along the direction of motion contract. The speed of light in empty space emerges as a constant that does not change with the motion of the source or the observer. This finding breaks with everyday intuition, but is supported by experiments that test the behavior of light and electricity at high speeds. Time and space are no longer independent quantities. Together, they form a four-dimensional entity space-time, in which events have coordinates that can change depending on the motion of an observer, while the underlying structure remains consistent. The next step is to understand gravity within this new framework. In Newton's picture, gravity is a force that acts instantaneously at a distance, pulling masses toward one another. That idea fits poorly with special relativity, which does not allow signals to travel faster than light. Einstein searches for a new description that removes instantaneous action at a distance and preserves the constant speed of light. After years of work, he arrives at the theory of general relativity. In this theory, gravity is not a separate force in the old sense. Instead, mass and energy curve space-time and objects move along paths determined by this curvature. A planet in orbit is not being pulled sideways by an invisible force. It is following the nearest equivalent of a straight line in a space-time that is curved around the central mass. Light, which must travel along the shortest possible paths in space-time, also responds to this curvature. When a beam of light passes near a massive object like the sun, its path should bend slightly. This bending of light offers a direct way to test general relativity. During an ordinary day, the sun's glare hides background stars, making such a test impossible. A total solar eclipse, however, briefly blocks the sun's bright disk and reveals the field of stars near its edge. Einstein calculates that starlight passing close to the sun should be deflected by a specific small angle. If the positions of stars on the sky are measured during an eclipse and compared with their positions at night when the sun is elsewhere, any difference might reveal this bending. In 1919, an international effort led by Arthur Eddington and others observes a total solar eclipse from different locations, including sites in Brazil and on an island off the coast of Africa. Plates taken during the brief period of totality capture the positions of stars near the darkened sun. Months of careful measurement and comparison follow. The shifts in position appear to match the predictions of general relativity within the uncertainties of the instruments. Starlight has curved as it passes the sun. News of this result spreads quickly. Newspapers announce that Newton's ideas have been overturned and that a new theory of the universe has taken their place. The public attention focuses on Einstein as a symbol of this change, but the deeper shift lies in the nature of space and time themselves. The universe is no longer a static stage equipped with absolute space and absolute time. It is a dynamic entity in which geometry and gravity are linked. Matter tells space-time how to curve, and curved space-time tells matter how to move. This framework can describe planetary orbits, the precession of Mercury's path, and the bending of light. It can also be applied to the entire universe as a single geometric object. When general relativity is used to model the cosmos as a whole, a striking result appears. If space is filled with matter, and if space-time responds to that matter according to Einstein's equations, then a perfectly static universe is not stable. In almost all simple models, the universe must either expand or contract. This behavior echoes the earlier concerns about the instability of an infinite Newtonian universe, but now it arises from the geometry of space-time itself, rather than from simple force arguments. A uniform distribution of matter in a curved space-time tends to evolve. If the universe begins slightly larger or smaller than a critical size, it cannot simply remain fixed. Gravity drives it one way or the other. Einstein is reluctant to accept a changing universe. Observations at the time do not clearly show any large-scale expansion or contraction. The Milky Way is still commonly regarded as the entire universe, and the nature of distant nebulae is uncertain. The philosophical and scientific culture of the period still leans toward a cosmos that is essentially static on the largest scales. To reconcile his equations with a static universe, Einstein introduces an additional term into the field equations of general relativity. This term, known as the cosmological constant, acts as a form of energy associated with empty space itself. It produces a subtle repulsive effect that can counterbalance the attractive pull of matter under gravity. By tuning the value of this constant, it becomes possible to construct a solution in which the universe remains static on average, with space-time curved in such a way that the gravitational tendency to collapse is exactly balanced by the repulsive effect of the cosmological constant. This static solution satisfies the desire for a calm universe that neither expands nor contracts. It allows general relativity to coexist with the prevailing view of the cosmos. However, later analysis shows that this balance is also unstable. A slightly larger or smaller universe would cause the repulsive and attractive effects to fall out of balance, leading again to either expansion or contraction. The apparent stability is fragile. Even so, the introduction of the cosmological constant leaves a lasting mark. It treats empty space as something that can have energy and can influence the dynamics of the universe, not just a passive nothingness in which events occur. At this point, general relativity provides a powerful new way to think about the cosmos. Space and time are linked. Gravity is geometry, and the energy of matter and radiation determines the large-scale structure of space-time. Yet the actual structure and history of the universe remain uncertain. Are the faint nebulae seen through telescopes distant systems of stars outside the Milky Way? Or are they clouds within it? Is space finite or infinite, positively curved like the surface of a sphere, negatively curved like a saddle or flat, in the sense described by Euclidean geometry? Does the universe change with time, or is any change confined to local processes within an unchanging cosmic background? General relativity opens the door to answers, but those answers depend on observations that have not yet been made. The bending of light by the sun confirms the theory on solar system scales, yet says nothing directly about the size, shape, or age of the universe. Mathematical solutions of Einstein's equations suggest that dynamic universes which expand or contract are natural outcomes. Some theorists explore such expanding models even before the key observations are in place. However, the static solution with a cosmological constant remains attractive because it preserves the familiar idea of an eternal universe while still incorporating the new physics of curved spacetime. The instability of this static configuration is understood only gradually and does not immediately dominate the discussion. Meanwhile, the observational side of astronomy continues to improve. Larger telescopes, better photographic plates, and more sensitive instruments make it possible to study faint nebulae in greater detail. Spectra reveal characteristic patterns of absorption and emission lines that can be used to estimate velocities through the Doppler effect. These measurements show that many nebulae, if interpreted as collections of stars, are moving relative to the Milky Way at significant speeds. Some appear to be receding from us. Yet, without accurate distances, these speeds are hard to place in a cosmic context. The question of whether the universe as a whole is expanding, contracting, or static cannot be answered until astronomers can measure how far away these objects are. The stage is therefore set for a convergence. On one side, general relativity insists that a static universe is unnatural and probably unstable. On another side, traditional assumptions and incomplete data support the idea of a calm, eternal cosmos. In between, a growing set of observations hints that the universe is larger and more complex than once thought, possibly populated by many star systems far beyond the Milky Way. The resolution will come when a method for measuring distances to distant galaxies is combined with spectral measurements of their motion. When that happens, the universe will no longer be able to hide its large-scale behavior. The static model that required the cosmological constant will be replaced by a dynamic view, and the question of a beginning will return with renewed force, now expressed in the language of curved space-time and cosmic expansion rather than in myth or pure philosophy. At the beginning of the 20th century, astronomy gains new tools for measuring the sky, and a quiet revolution begins with the careful study of starlight on photographic plates. At the Harvard College Observatory, a group of women, known informally as computers, examined thousands of glass plates recording the brightness and positions of stars with patience and precision. Among them, Henrietta Swan Leavitt studies a class of stars whose brightness varies over time. These are Cepheid variable stars, large luminous stars that rhythmically brighten and fade over periods ranging from a few days to several months. As Leavitt compares the light curves of many such stars in the small Magellanic Cloud, she notices a striking pattern. The longer the period of a Cepheid's pulsation, the intrinsically brighter the star must be. Because the stars in that cloud are roughly at the same distance from Earth, differences in their apparent brightness can be interpreted as differences in true luminosity. Leavitt's period luminosity relation provides a new kind of tool. If an astronomer observes a Cepheid variable in another system, measures how long it takes to cycle from bright to dim and back again, and then uses Leavitt's relation to estimate how luminous the star really is, the difference between that intrinsic brightness and the observed brightness yields a distance. For the first time, there is a reliable way to measure distances to certain very bright stars far beyond the reach of previous methods. This distance ladder soon extends the scale of the known universe. Edwin Hubble, working with the Large Telescope at Mount Wilson Observatory, turns his attention to some of the mysterious nebulae that have puzzled astronomers for decades. Among these, the Andromeda Nebula stands out as a large, faint, spiral-shaped object whose nature is uncertain. Some astronomers believe it to be a nearby cloud of gas within the Milky Way. Others, inspired by earlier philosophical suggestions, suspect it might be an entire separate star system, an island universe. By searching carefully within Andromeda for variable stars, Hubble identifies Cepheids and measures their periods. Applying Leavitt's relation, he estimates their luminosities and thus their distance. The result places Andromeda far beyond the expected size of the Milky Way. The object is not a local cloud within our galaxy, but a separate galaxy, composed of its own stars, separated from the Milky Way by a vast intergalactic space. Similar measurements for other nebulae reveal that many of them are also distant galaxies. The scale of the universe expands dramatically. What once seemed like the entire cosmos, the Milky Way becomes one galaxy among many. While these distance measurements unfold, another line of evidence emerges from the study of spectra. Vesto Slipher at Lowell Observatory measures the spectral lines of light from various spiral nebulae. By comparing the positions of absorption and emission lines to those seen in laboratory spectra, he finds that many of these lines are shifted toward the red end of the spectrum. This redshift can be interpreted as a Doppler effect, indicating that the sources are moving away from Earth at high speeds. A few objects show blue shifts, suggesting motion toward us, but the majority display red shifts with recession speeds of hundreds of kilometers per second. At first, these measurements are puzzling, but not immediately connected into a larger pattern. As Hubble continues to collect distance estimates to galaxies using Cepheids and combines them with redshift data from Slipher and others, a trend becomes clear. When distances are plotted against recession speeds, the data cluster around a simple relation. More distant galaxies, on average, are receding faster. The simplest interpretation is that space itself is expanding, carrying galaxies apart over time. In this picture, galaxies are not moving through a fixed static space like projectiles in an empty room. Instead, the distances between them grow because the underlying fabric of space-time stretches. On large scales, every distant galaxy appears to recede from any chosen vantage point with a speed roughly proportional to its distance. This is consistent with general relativity, which permits solutions in which the universe expands uniformly. The observation that more distant galaxies recede more rapidly therefore fits naturally into the framework Einstein developed, even though he had initially introduced the cosmological constant, partly to avoid such a dynamic cosmos. The old static universe begins to give way. The Milky Way becomes one galaxy among billions, and the overall picture of the cosmos shifts from a timeless structure to an evolving one. If the universe is expanding today, then at earlier times it must have been smaller and denser. The linear relationship between distance and recession speed implies that by running the expansion backward, one could, in principle, reach a time when the separation between galaxies shrinks toward zero. This is not merely a matter of galaxies approaching each other. Because space-time itself evolves, the entire large-scale structure of the universe appears to have emerged from a much more compact, hotter state. The expanding universe solutions of general relativity, developed independently by Alexander Friedmann and Georges Lemaitre, provide mathematical support for this idea. Friedmann derives models in which the scale of the universe changes with time under the influence of gravity and possibly the cosmological constant. Lemaitre, a physicist and priest, connects these mathematical models with observational data, arguing that the observed redshifts of galaxies can be understood as evidence for an expanding universe. He also introduces the idea that the observable universe might have emerged from an initially extremely dense state, which he describes in terms that evoke a primeval atom. In this picture, the universe does not simply exist eternally in a static form. It has a history in which matter and radiation evolve as space expands. Despite these developments, the emerging view of an expanding, evolving universe faces challenges. One issue concerns the age of the cosmos inferred from the expansion rate. Early estimates of the proportionality between distance and recession speed suggest an expansion age of the order of 1 to 2 billion years. Geological and astronomical evidence from the study of Earth's rocks and radioactive decay, as well as from stellar evolution, indicate that the Earth and many stars are significantly older than this. The mismatch implies that either the expansion rate is mismeasured, the theoretical assumptions are incomplete, or the interpretation of the redshift distance relation needs refinement. As measurements improve, distance estimates to key galaxies such as Andromeda are revised, and the derived age of the universe increases, alleviating the tension. Nevertheless, the episode shows how a simple, appealing picture of an expanding universe immediately raises questions about consistency with other lines of evidence. The discovery of cosmic expansion also forces a re-examination of Einstein's cosmological constant. In a universe that expands, a carefully tuned constant is no longer needed to maintain static balance. Einstein reportedly regards his introduction of this term as an error, though the idea that empty space might have its own energy will later return in a different context. For now, the focus is on understanding the implications of an expanding universe filled with matter and radiation. If space is enlarging and galaxies are moving apart, then at earlier times, everything must have been closer together. As the universe is traced back, the average density of matter increases, and so does the temperature of any radiation-filling space. This leads naturally to the concept of a hot, dense early universe. In such a state, atoms cannot remain bound. Matter exists as a mixture of nuclei, electrons, and photons in a tightly coupled plasma. When cosmologists reconstruct this scenario, they realize that it offers testable predictions. The early universe, if hot and dense enough, should have undergone nuclear reactions similar to those in the cores of stars producing light elements in specific ratios. It should also have left behind a relic glow of radiation stretched and cooled by subsequent expansion, but still present as a faint background. The expanding sky has thus transformed a philosophical question about beginnings into a concrete physical framework. From Cepheid variables and galactic redshifts to relativistic cosmology, the evidence points toward a universe that had a younger, hotter, denser phase. The exact nature of the initial state remains uncertain. Some imagine a singular point where densities and curvatures become infinite, while others suspect that this is only a sign that the current theories break down at very high energies. Either way, the combination of theory and observation now supports a clear claim. The universe, as observed today, has not always existed in its present form. It has expanded and cooled over billions of years from a very different early state. The next step is to examine the traces left by that state in the composition of matter and in the faint light that pervades all of space, and to see whether they confirm or challenge the picture of a hot, dense beginning. As the idea of an expanding universe settles into cosmology, attention turns to what conditions must have prevailed when everything was closer together and hotter. If galaxies are now receding from one another and space is stretching, then in the remote past, the average density of matter and the temperature of any radiation filling space must have been far higher than they are today. This realization allows physicists to connect cosmic history with laboratory physics. The behavior of matter at high temperature and density is already studied in the context of stellar interiors and nuclear reactions. Those tools can now be applied to the early universe itself. George Gamow, Ralph Alpha, and their collaborators imagine an early phase in which the universe consists of a hot, dense mixture of protons, neutrons, electrons, and light. In such conditions, ordinary atoms cannot exist as bound structures. Nuclei and electrons are separated by frequent energetic collisions, and photons of light scatter constantly from charged particles, keeping everything tightly coupled. As the universe expands, this plasma cools. Nuclear reactions among protons and neutrons can briefly occur as temperatures fall through a critical range. The result is a process sometimes called primordial nucleosynthesis, during which light elements are forged. The calculations indicate that under reasonable assumptions about the density of matter and the rate of expansion, most of the ordinary matter in the universe should emerge from this early phase in the form of hydrogen nuclei with a significant fraction locked into helium and a trace amount forming isotopes like deuterium and elements, such as lithium. When the predicted proportions are worked out, they suggest that roughly 3/4 of the mass in ordinary matter should be hydrogen and about 1/4 helium, with far smaller contributions from everything else. Astronomers can test this prediction by examining the chemical composition of very old stars and diffuse gas clouds that have not been heavily processed by repeated cycles of star formation and destruction. Observations show that the universe does indeed contain a high fraction of helium, too large to be explained solely by fusion inside stars over the available time. The pattern of abundances for hydrogen, helium, and the lightest elements lines up well with what primordial nucleosynthesis in a hot early universe would produce. This agreement does not prove every detail of the model, but it supports the central claim that the universe once passed through a phase hot and dense enough for nuclear reactions to shape its basic composition. The same early phase should also leave a different kind of trace. In the hot plasma, photons of light are constantly scattered, absorbed, and re-emitted by the charged particles around them. The radiation stays in almost perfect thermal equilibrium, meaning that its energy distribution follows a specific pattern determined solely by temperature, known as a black-body spectrum. As expansion continues and the universe cools, there comes a point when the average energy of the photons is no longer high enough to keep electrons and nuclei apart. Protons and helium nuclei capture electrons to form neutral atoms. With far fewer free charged particles available, photons can finally travel long distances without constant scattering. They decouple from matter and begin to stream freely through space. This transition occurs when the universe has cooled to a few thousand degrees hundreds of thousands of years after the earliest nuclear reactions. From that time onward, the radiation released at decoupling continues to fill space. As space expands, the wavelengths of these photons are stretched and their average energy decreases. A black body spectrum at a high temperature is transformed into a black body spectrum at a much lower temperature. If the hot early universe picture is correct, there should exist today a faint background of microwave radiation coming from all directions, with a nearly perfect black body spectrum and a temperature only a few degrees above absolute zero. Hints of such a background appear in mid-20th century observations, though they are not initially recognized for what they are. Andrew McKellar, studying interstellar molecules, infers that the space between stars effectively corresponds to a temperature of a few degrees above absolute zero. This result is remarkable, but remains an isolated finding, not yet connected to a full cosmological context. In parallel, theoretical work by Alpha Robert Herman and others anticipates that a relic radiation field should exist if the universe began in a hot, dense state. They estimate its temperature to be a few degrees above absolute zero, matching the general scale later inferred from observations. Direct detection comes somewhat unexpectedly. At Bell Laboratories, Arno Penzias and Robert Wilson use a sensitive microwave antenna to study radio emission from the Milky Way and from communication satellites. Their instrument detects a persistent background noise that cannot be eliminated. It does not vary with direction on the sky, with time of day, or with the season. After ruling out many possible sources, including instrumental effects and nearby interference, they learn of work at Princeton University, in which researchers are preparing an experiment specifically designed to search for the predicted background radiation from the early universe. The properties of the unexplained noise in the Bell Lab's antenna match the expected characteristics of this relic glow. The conclusion emerges that the observed microwave background is the cooled remnant of the radiation that filled the hot early universe at the time when atoms first formed. Subsequent measurements refine this picture. The spectrum of the background is measured with high precision and found to match that of an almost perfect black body at a temperature of about 3 degrees above absolute zero. Among all known physical systems, this cosmic microwave background has one of the most precisely black body spectra ever observed. The uniformity of its temperature across the sky is also striking. Measurements show that after subtracting the effect of the motion of the Earth in the solar system, the temperature is nearly the same in every direction, with only very small fluctuations. Satellite missions such as the Cosmic Background Explorer map the microwave sky in detail. They confirm both the black body nature of the spectrum and the existence of tiny variations in temperature and intensity at different points on the sky. These variations are extremely small, but they are significant. They indicate that the early universe was not perfectly uniform. Slightly denser and slightly hotter regions existed alongside slightly less dense and cooler regions. Over billions of years, these small initial differences could grow under the influence of gravity to form the large-scale structure observed today, including galaxies, clusters, and extended patterns of matter. Taken together, the success of primordial nucleosynthesis and the detection of the cosmic microwave background create a robust framework. The expanding universe is not just an abstract solution of general relativity. It is a specific physical history in which a hot, dense early phase leaves measurable imprints on the composition of matter and on the radiation that permeates space. The match between theoretical predictions and observations suggests that the broad outlines of this story are correct. There was indeed a time when the universe was much hotter and denser, when nuclear reactions set the ratios of light elements, and when radiation and matter formed a tightly coupled plasma whose decoupling produced a relic glow still visible today in the microwave part of the spectrum. Yet even as this picture gains strength, it reveals new puzzles. The microwave background is astonishingly uniform across the sky, even in regions that under simple assumptions could not have exchanged light or heat before the time of decoupling. The overall geometry of space appears to be very close to flat, despite theoretical expectations that such a state should be unstable. Particle physics suggests that exotic relics should have formed in the hot early universe, but they are not observed in the abundance one might expect. The same observations that confirm a hot, dense beginning therefore point toward questions that the simple Big Bang model taken by itself cannot easily answer. These questions do not overturn the evidence for a hot early phase, but they suggest that the history of the universe before the first well-described second is more complex than a straightforward extrapolation back to a single moment of infinite density. With the broad success of the hot early universe picture, cosmology gains a clear narrative for how matter and radiation evolve after a certain point. The ratios of light elements match expectations from nuclear reactions in a dense plasma. The cosmic microwave background displays the temperature and spectrum expected from radiation released when atoms first formed. Galaxies and clusters can grow from small initial irregularities over long periods under the influence of gravity. Yet this apparently coherent story contains internal tensions that become sharper as measurements improve. The more precisely astronomers and physicists look, the more they find that the early universe seems almost unnaturally well prepared. One of the clearest tensions is called the horizon problem. The cosmic microwave background shows that the temperature of the radiation is nearly the same in every direction. After subtracting the modest effect of the Earth's motion, the variations are tiny, a fraction of a percent. This level of uniformity suggests that the regions of space that emitted the radiation must have come to a common temperature before they released their light, which implies that they were once in causal contact, exchanging energy and information. In simple, expanding universe models, without any additional early phase, there is not enough time before the moment when atoms form and photons decouple for widely separated regions to influence one another. Light can only travel a finite distance in a given time, so there is a maximum scale over which temperatures could have evened out. Yet, when the microwave background is mapped, the uniformity extends across patches of sky that correspond to regions far larger than this causal scale. Points on opposite sides of the sky, which appear not to have shared any common past within the framework of the basic Big Bang model, exhibit almost identical temperatures. It is as if distant parts of the universe agreed on a common condition without having had the opportunity to communicate according to the usual rules of relativity and light travel. A second tension is known as the flatness problem. General relativity allows the geometry of space on large scales to be positively curved, negatively curved, or nearly flat. This geometry can be described in terms of how the density of matter and energy compares to a critical value determined by the expansion rate. If the total density is higher than this critical value, the universe is positively curved somewhat like the surface of a sphere. If it is lower, the universe is negatively curved somewhat like a saddle. If it matches exactly, the universe is spatially flat in the sense that parallel lines remain parallel. In the standard hot Big Bang model, the density and the expansion rate evolve with time, and any slight deviation from the critical density tends to grow as the universe expands. This means that if the density today is close to the critical value, as observation suggests then in the early universe, it must have been incredibly, almost unimaginably close to that value. Even a tiny difference would have grown over billions of years into a large departure from flatness. The requirement that the early universe be tuned to such extraordinary precision is troubling. It raises the question of why the initial conditions should have been set so delicately. Some physicists are willing to accept this as a fact about the universe, while others suspect that some missing mechanism might drive the density toward the critical value, rather than requiring it to start there. A third puzzle arises from particle physics. Theories that extend the standard description of fundamental forces suggest that at the extremely high temperatures of the very early universe, a variety of heavy exotic particles should have been produced. Among these hypothetical relics are magnetic monopoles, particles that carry a single magnetic charge north or south, rather than the paired poles seen in ordinary magnets. If such particles were created copiously in the hot, dense phase, they should still be present in significant numbers today because they would be very hard to destroy once the universe cools. Yet, careful searches have failed to find any convincing evidence for magnetic monopoles in the expected abundance. The absence of these relics is called the monopole problem. It suggests either that the conditions that would create them never existed, or that some process diluted them to a negligible level. The horizon flatness and monopole problems all point toward a common theme. The simple extrapolation of the hot Big Bang model back toward earlier and earlier times seems to produce either special initial conditions or unwanted relics. The picture works extremely well from a short time after the release of the microwave background onward, but the conditions at earlier times appear increasingly contrived or unstable. On top of these issues, there is the question of the initial singularity itself. Theorems developed by Stephen Hawking, Roger Penrose, and others analyze the behavior of space-time under general relativity when certain conditions are assumed. If gravity is always attractive in a specific technical sense, if space-time satisfies reasonable energy conditions, if there are no closed loops in time, and if general relativity remains valid all the way down to arbitrarily small scales, then the theorems indicate that the expanding universe must originate from a past boundary where curvature and density become infinite. This boundary is not part of space-time in the usual sense. It marks a limit beyond which the theory cannot describe events. In this scenario, the Big Bang is not just a very dense state, but a true edge to space-time, a place where the concept of time itself ceases to be meaningful. However, the assumptions behind these theorems are precisely the ones that may break down in the extreme conditions near the alleged singularity. At very high energies and very small scales, quantum effects become important, and general relativity, which treats space-time as a smooth classical geometry, is expected to be incomplete. Quantum field theory, which successfully describes particle physics in flat space-time, on the other hand, is not yet consistently unified with gravity. The absence of a full quantum theory of gravity means that any conclusions about what happens at the highest densities must be tentative. Both Hawking and Penrose later acknowledge that the singularity theorems signal the breakdown of classical theory, rather than a definitive description of a physical beginning of time. This situation leaves cosmologists in an interesting position. On the one hand, there is strong evidence for a hot, dense phase for primordial nuclear reactions, and for a relic radiation field that has cooled to microwave temperatures. On the other hand, the underlying model that extrapolates this phase all the way back to a singular origin faces conceptual and observational difficulties. The uniformity of the microwave background across regions that should not have equilibrated the extreme fine-tuning required to keep the geometry close to flat, and the missing heavy relics all suggest that something significant is missing from the simplest version of the story. Various alternative ideas are explored. Some theorists propose models in which the universe undergoes cycles of expansion and contraction. In such bouncing models, what appears to be a beginning could be a transition between a prior contracting phase and the current expanding one. Others modify the behavior of gravity at very early times, or introduce new fields that might alter the dynamics. These approaches differ in detail, but many share a common goal. They seek to explain the observed uniformity and near flatness of the universe and the absence of unwanted relics without requiring initial conditions to be tuned with extraordinary precision. As these efforts proceed, attention returns to the role of vacuum energy, the energy associated with empty space itself. The cosmological constant, once introduced by Einstein to support a static universe and later regarded as unnecessary, is recognized as a special case of such energy. Quantum field theory indicates that even in the lowest energy state, a field in empty space has fluctuations and zero-point energy. In ordinary conditions, these effects are too small or too evenly distributed to have an obvious impact. In the early universe, however, vacuum energy could play a dominant role. A region of space filled with a field in a high-energy configuration might experience a form of negative pressure that drives rapid expansion. This idea connects the earlier puzzles in a new way. If at some very early stage the universe entered a phase in which the energy of a field in the vacuum dominated everything else, it might expand much faster than in the standard radiation or matter-dominated eras. Such a rapid expansion could stretch any initial irregularities, dilute heavy relics, and drive the curvature of space toward flatness. It could also enlarge a tiny region that was once small enough to come into thermal equilibrium into a vast domain that later becomes the observable universe, thereby explaining the uniformity of the microwave background. These possibilities lead to the development of inflationary cosmology, in which an early period of accelerated expansion reshapes the naive picture of the Big Bang. In inflationary models, the hot, dense phase that produces nucleosynthesis and the microwave background is not the absolute beginning, but rather a transition following an earlier phase driven by a nearly constant vacuum energy. The familiar Big Bang becomes, in a sense, the end of inflation, rather than the start of everything. Before that end, space may have been expanding at an enormous rate, smoothing and flattening the region that will later evolve into the observable universe. The horizon flatness and monopole problems thus serve as signposts pointing beyond the simple hot Big Bang toward a richer story in which the first detectable second of cosmic history is preceded by processes that leave subtle but decisive imprints on what is seen today. The idea that vacuum energy might drive a rapid expansion of the early universe becomes concrete when physicists study phase transitions in quantum fields. In ordinary matter, a phase transition occurs when a system changes from one state to another, such as ice melting into liquid water or liquid water boiling into steam. These changes involve shifts in energy and structure that depend on temperature and pressure. Quantum fields, which underlie particles and forces, can also undergo transitions between different energy configurations. At very high temperatures, such as those in the early universe, fields may be trapped in a higher energy state that is temporarily stable, a kind of plateau in the energy landscape. As the universe cools, the field can transition to a lower energy state, releasing energy in the process. Alan Guth, working in the late 20th century, examines how such transitions might have shaped cosmic history. He considers a situation in which a field associated with a unified force of nature is stuck in a metastable high-energy state, sometimes called a false vacuum. In this state, the energy density of the field remains nearly constant as space expands. In general relativity, a constant positive energy density in empty space acts like a cosmological constant. It produces a negative pressure that drives accelerated expansion. Guth realizes that if the universe ever entered such a false vacuum phase, the expansion would not proceed at the steady rate of a radiation or matter-dominated cosmos. Instead, it would accelerate, causing the scale of the universe to grow exponentially. Distances between points would double and redouble over extremely short intervals of time. In a tiny fraction of a second, a region that was initially small enough to be causally connected could become vastly larger than the observable universe today. This inflationary behavior has several important consequences for the puzzles identified earlier. First, consider the horizon problem. If a small region of space was once in local thermal equilibrium, its temperature would have been smoothed out by ordinary physical processes. If that region then underwent an enormous accelerated expansion, it could grow to encompass an area that appears in the later universe as many widely separated regions on the sky. Those regions would share a common temperature because they originated from the same causally connected patch. Light would not need to travel between distant points after the time of decoupling to equalize temperatures. The equalization would have occurred before inflation, and the expansion would simply carry that uniform state to much larger scales. In this way, a brief early epoch of inflation can explain why the cosmic microwave background has nearly the same temperature in directions that simple Big Bang models would treat as causally disconnected. Next, consider the flatness problem. The geometry of space in general relativity responds to the total energy density and pressure. In an inflationary phase dominated by a constant vacuum energy, space expands so rapidly that any initial curvature is driven toward zero within the region undergoing inflation. A useful analogy from everyday life is stretching a curved surface until it looks flat over a small area, but in the inflationary context, This effect is quantitative and built into the equations. As the scale factor of the universe grows by many orders of magnitude, the deviation of the density from its critical value shrinks toward zero. By the time inflation ends, the region that will become our observable universe is extremely close to spatial flatness regardless of its initial geometry. Subsequent evolution during radiation and matter-dominated eras can then proceed without significant departure from flatness, naturally producing the nearly critical density observed today without requiring precise tuning at the earliest times. The monopole problem is addressed in a different way. Heavy relic particles, such as magnetic monopoles, would have been produced in great numbers if certain grand unified theories of particle physics accurately describe the conditions of the very early universe. However, if inflation occurs after their production, the rapid expansion dilutes their number density to negligible levels. The same exponential growth that stretches space to near flatness also stretches any population of relic particles over such an immense volume that within the region that later becomes the observable universe, they are effectively absent. In some versions of inflation, the transition from the false vacuum to the true vacuum occurs early enough that monopoles are not produced in large quantities within our patch at all. In either case, inflation offers a natural mechanism to remove or dilute unwanted relics without special initial conditions. Guth's original model uses the concept of supercooling, where the field remains in the false vacuum state even as the universe cools below the temperature at which a transition to the true vacuum would normally occur. Eventually, bubbles of the lower energy phase would nucleate and grow, converting the false vacuum energy into particles and radiation. However, this first version of inflation faces difficulties. If the transition proceeds through rare bubble formation in an otherwise rapidly expanding false vacuum, the bubbles may fail to percolate and merge efficiently. The result could be a universe dominated by regions that remain inflating, with isolated true vacuum bubbles that never collide in the right way to form a homogeneous hot phase like the one inferred from observations. To address these issues, other physicists propose refinements such as new inflation and chaotic inflation, in which the inflating field, the field driving inflation, evolves smoothly down a potential energy curve rather than tunneling abruptly. In these models, inflation can end more gracefully, with the field rolling into a lower energy state across an extended region, converting vacuum energy into a thermal bath of particles and radiation in a process sometimes called reheating. The key feature is that inflation provides a bridge between a vacuum-dominated phase and the familiar hot Big Bang phase. After inflation ends, the universe is filled with a dense hot plasma of particles and radiation from which nucleosynthesis and the formation of the cosmic microwave background proceed in the usual way. In this revised picture, the Big Bang, as traditionally described, is not the origin point of spacetime, but a transition from inflationary expansion to a radiation-dominated era. The hot, dense beginning is real, but it is reinterpreted as the aftermath of inflation rather than as an absolute starting singularity. Inflation not only solves conceptual problems, it also makes new predictions. The inflating field is a quantum field subject to fluctuations. Even in a vacuum state, quantum fields undergo random variations about their average values. During inflation, these tiny fluctuations are stretched to macroscopic scales by the rapid expansion. When inflation ends and the inflaton decays into ordinary particles, the imprinted fluctuations become small variations in the density and temperature of the plasma. These irregularities are expected to be nearly scale invariant, meaning that their statistical properties change only slowly with length scale. They should also be approximately Gaussian in the sense that their distribution can be described by simple random processes. The tiny hot and cold spots observed in the cosmic microwave background fit these expectations remarkably well. Their spectrum of fluctuations as measured by satellites and ground-based experiments matches the patterns predicted by simple inflationary models within observational uncertainties. This agreement strengthens the case that inflation, or something very much like it, occurred in the early universe. Yet, the detailed nature of the inflaton field remains unknown. Different theoretical frameworks suggest different candidates with various shapes for the potential energy curve. In some models, the inflaton is related to fields that break grand unified symmetries. In others, it is a more abstract scalar field introduced specifically to drive inflation. Some versions require fine-tuning of parameters to match observations. Others attempt to reduce such tuning by linking inflation to known physics. There is not yet a single universally accepted model. Furthermore, when the dynamics of inflation are studied carefully, a striking implication emerges. In many models, inflation does not end everywhere at once. Quantum fluctuations in the inflaton field cause different regions of space to exit the inflationary phase at slightly different times. Some areas roll down the potential energy slope and reheat, forming hot Big Bang patches, like the one that gives rise to our observable universe. Other regions remain in the false vacuum or on a high plateau for longer, continuing to inflate. In such scenarios, inflation becomes eternal to the future. While it ends locally in finite pockets, it continues indefinitely in other regions, constantly spawning new domains where hot Big Bang conditions arise. This picture suggests that our observable universe may be one bubble among many in a much larger, inflating space-time. Each bubble can have its own realization of initial conditions and, in some models, even different low-energy physical properties. This is the beginning of the multiverse idea in an inflationary context. Inflation thus transforms the understanding of the Big Bang. The hot, dense phase is a real part of the universe's history, strongly supported by evidence, but it is no longer seen as an isolated, unexplained starting condition. Instead, it may be the outcome of a prior inflationary epoch driven by vacuum energy. The puzzles of horizon flatness and relics find natural explanations, and the small variations that seed cosmic structure arise from quantum fluctuations in a field that once dominated the energy density of the cosmos. At the same time, inflation raises new questions. What exactly is the inflaton field, and how is it connected to known particles and forces? Why did it take the particular form that produced the observed fluctuation spectrum and energy scale? Did inflation truly begin at some finite time, or is it past eternal in some generalized sense? These questions push beyond the comfortable territory of the hot Big Bang into a less certain domain where quantum gravity, high-energy physics, and cosmology intersect. The Big Bang theory, as originally taught, did not attempt to explain what banged or why. Inflation begins to address that question, suggesting that what banged was the sudden end of a vacuum-dominated phase, releasing energy into matter and radiation. But the origin of that phase and of the conditions that allowed it remains open. When inflation ends and its energy is converted into a hot bath of particles and radiation, the universe enters the familiar Big Bang phase, but it does not emerge perfectly smooth. Quantum fluctuations in the inflaton field stretch to astronomical scales during the inflationary expansion become slight variations in the density and temperature of the primordial plasma. In some regions, the density is a tiny bit higher than average, in others, a tiny bit lower. These differences are incredibly small, but gravity is sensitive even to slight imbalances. Over time, regions that start out a little denser pull in more matter, becoming denser still, while underdense regions lose material to their surroundings. In this way, the microscopic quantum jitter of a field in the very early universe seeds the macroscopic structure of everything that comes later. The cosmic microwave background provides a direct view of these initial irregularities. When atoms first form and photons decouple from matter, the pattern of slightly hotter and cooler spots in the radiation reflects the density variations in the plasma at that time. Satellites that map the microwave sky measure fluctuations in temperature that are only tens of millionths of a degree above or below the average, yet these tiny variations carry a detailed record of the early universe's conditions. By analyzing how the strength of fluctuations changes with angular scale on the sky, cosmologists reconstruct the spectrum of primordial density perturbations. The observed spectrum is close to scale invariant, as inflationary models predict, meaning that fluctuations have almost the same amplitude over a wide range of length scales, with a slight tilt that carries information about the inflaton potential. The pattern of peaks and troughs in the fluctuation spectrum also reveals an important piece of physics. Before decoupling, the primordial plasma behaves like a fluid of photons and baryons, ordinary matter, in which pressure from radiation resists compression while gravity tries to pull matter into denser clumps. This competition produces acoustic waves oscillations in density that leave characteristic imprints on the microwave background. At the moment of decoupling, some regions happen to be at maximum compression, others at maximum rarefaction, and still others in intermediate states. These frozen oscillations show up as a series of peaks in the power spectrum of temperature fluctuations, each corresponding to a different harmonic of the primordial sound waves. The positions and heights of these peaks are sensitive to the total matter density, the fraction of ordinary matter versus dark matter, and the curvature of space. Measurements of the microwave background therefore constrain the composition and geometry of the universe as well as the properties of the initial perturbations. After decoupling, the evolution of structure continues. The photons stream away freely, forming the cosmic microwave background we observe today, while matter, now mostly neutral, feels gravity more directly. Regions that were slightly overdense grow into larger structures as they attract surrounding material. Dark matter, which interacts weakly with radiation and ordinary matter, but contributes mass and gravity, plays a crucial role. It begins to clump earlier than baryons, forming gravitational wells into which gas later falls. Over billions of years, these wells deepen and structures form hierarchically. Small objects collapse first, then merge into larger ones, creating galaxies, groups, and clusters. On the largest scales, the distribution of matter becomes a vast cosmic web of filament sheets and voids. Galaxies gather along filaments like beads on threads, while great empty regions span tens of millions of light-years between them. Large galaxy surveys, which map the positions and redshifts of millions of galaxies, reveal this web in detail. When the statistical properties of the cosmic web are compared with simulations that start from inflationary initial conditions and evolve matter forward under the influence of gravity, the match is striking. The same nearly scale invariant spectrum of fluctuations that appears in the microwave background when used as input for computer models grows into a network of structures that resembles what telescopes see. The alignment between theory, simulation, and observation strengthens the link between quantum fluctuations in the early universe and the large-scale arrangement of galaxies today. Yet this apparent success carries a subtle and unsettling implication. If the positions of galaxies, clusters, and even future stars and planets trace back to random quantum fluctuations in the inflating field, then the detailed layout of cosmic structure is contingent on chance at a very deep level. Within the inflationary framework, the overall statistical properties of the fluctuations are determined by the physics of the field and its potential. But the specific realization, the exact pattern of highs and lows, is random. This means that the existence of particular features, such as a certain supercluster or a specific large void near the Milky Way, is not in